Hello, and welcome to Ray Tracing Performance Revealed. I'm Chris Hessick, and I will be joined later by John Alper. In this talk, we will discuss the features in the Radeon GPU Profiler that can be used to analyze and optimize the use of ray tracing in a game. We'll also be showing a preview of the Radeon Ray Tracing Analyzer, a brand new tool we've been working on. The first part of this video will focus on the Radeon GPU Profiler, or RGP. RGP is a frame-based GPU performance analysis tool. It exposes hardware-level profiling data, which allows a developer to identify bottlenecks in a DirectX 12 or Vulkan game. Providing intuitive visualizations and easy-to-use workflows, RGP can help you optimize your game to run on AMD GPUs. For this video, we will focus on features in RGP that provide insight into the performance of ray tracing in a game's frame. We'll do this by showing how RGP can be used to answer specific performance questions that may be asked by a game developer. To get the most out of this talk, some familiarity with RGP is assumed. If you are unfamiliar with RGP, a good place to learn more is gpuopen.com, where you can find the RGP product page as well as articles and videos that discuss some of the main features of RGP. As a quick recap, RGP is made up of two types of views. First, we have the overview windows, which provide higher-level summary information about the captured frame. Second, we have the events views, which provide a much more detailed look into a frame's performance. In this outline, the views highlighted in red indicate which views specifically support the visualization and analysis of ray tracing events and workloads. As you can see, ray tracing is truly integrated into the RGP user interface and workflow. Now let's look at how the various views in RGP can be used to answer the key questions about ray tracing performance. We'll start with the overview windows, and then we'll look at the events windows. The first question a game developer might have is, which ray tracing events are the most expensive? To answer that question, we turn to the most expensive events overview window. This view lists the most expensive draw calls, dispatches, and other events in the frame. By expensive, we mean those that have the longest duration. To see which ray tracing events are the most expensive, simply sort this table by the API Shader Stages column. This will make sure that the most expensive ray tracing events are grouped together. Once you have done this, it becomes clear which ray tracing events are the most expensive and would be a good target for optimization efforts. Another way to look at a frame's performance would be to consider which ray tracing pipeline is the most expensive. This can be useful if more than one ray dispatch event uses the same ray tracing pipeline. In order to answer the question about which pipeline is the most expensive, a developer should turn to the Pipelines Overview window. Just like in the Most Expensive Events window, you can sort the pipelines by shader stage. Once you do that here, you can quickly see which ray tracing pipelines are the most expensive. In the case shown here, the most expensive pipeline is used by 3 separate events, and it also has the highest average event duration. This lets us know that this pipeline would be a good candidate for optimization. While the most expensive events and pipelines overview windows can provide a jumping-off point about where to focus optimization efforts, the events views will provide more detail about your frame and answer some more questions about your frame's ray tracing performance. Here we see the wavefront occupancy pane, where wavefronts from ray tracing events are colored in red. This view quickly answers the question of which parts of a frame are using ray tracing. The first bit of ray tracing work we see here is at the very beginning of the frame. This is the part of the frame where the acceleration structures are being built. Next, we see several larger red blocks later in the frame. These are a series of dispatch rays events which are performing the ray tracing in this frame. Once we've identified the ray tracing work in our frame, we may want to quickly check whether it fits our budgeted time for ray tracing. We can do that in the Event Timing view. To check the amount of time taken by ray dispatch calls, you can simply filter the events to only show dispatch rays calls. Once you do this, you can quickly see the amount of time taken for each of those events. In this case, we can see that the captured frame has 9 dispatch raise calls, and we can see the duration of each. By quickly doing the math, we can see that these 9 dispatch raise calls take about 15 milliseconds, which is likely over budget for our frame. Another question you may want to answer is related to the number of ray triangle and ray box tests performed by each ray dispatch. To see this, we can revisit the wavefront occupancy view and look at the ray tracing counters row. This is a new feature that is being added in an upcoming RGP release. By selecting a dispatch raise call, you can quickly see how many ray tests are performed, and you can see how those ray tests are distributed across the lifetime of the dispatch. In this screenshot, we see a selected region which corresponds to a single dispatch raise call. In the Ray Tracing Counters tooltip, we can see that this particular dispatch raise call performs 135 million ray box tests and 14 million ray triangle tests. For the next set of questions that RGP can help answer, we turn to the pipeline state view, which shows detailed information about the pipeline used for a specific ray tracing event. But first, a quick note on the 2 compilation modes that can be used by a dispatch raise event. The specific compilation mode used by a particular pipeline is chosen at runtime by the driver and compiler. First, there is the unified mode, where the individual shaders that make up the ray tracing pipeline are inlined into a single shader, resulting in a single stream of ISA. Second, there is the indirect mode, where the individual shaders are compiled separately, and each shader has its own distinct stream of ISA. In the indirect mode, the compiler generates function call instructions as needed to allow one function in the ray tracing pipeline to call another. When the indirect mode is used, the pipeline state pane in RGP can answer several key performance-related questions. First up, it can help answer questions about which specific stage of the ray tracing pipeline is the most expensive. This can be seen in the flowchart that represents the ray tracing pipeline. Here, each active stage in the ray tracing pipeline shows the relative cost associated with that stage. With a quick glance, you can quickly see which stage is the most expensive. In this case, as in many cases, the traversal stage has the highest cost. This is indicated by the red bar and the associated cost percentage shown in the traversal block within the flowchart. In addition to knowing which stage is the costliest, it can also be useful to know which specific shaders within a ray tracing pipeline are the most expensive. In order to answer this question, we turn to the shader table displayed below the flowchart. By default, this table is sorted by the instruction cost, so the most expensive shaders will be shown at the top of the table. The flowchart and the shader table can be used together to quickly narrow in on a shader to optimize. The flowchart is interactive in nature, allowing you to click a stage. This will filter the shader table to only show functions that correspond to the selected stage. This way, once you identify a stage to focus on, you can then look at the individual shaders that make up that stage. Here, we've decided to focus on the closest hit stage. By clicking that stage, we can quickly see which functions are part of that stage and also quickly see which shader within that stage is the most expensive. Once you've identified a particular shader as a bottleneck, you can turn to the instruction timing pane to dig deeper into that shader's performance. The instruction timing view correlates the disassembled ISA instructions for a shader to the low-level timing data collected from the hardware. It can then provide timing on a per instruction basis. The timing figures, shown here in the latency column, measure the issue latency between instructions. This is basically the number of clock cycles that elapsed between the current instruction being issued and the next instruction being issued. By default, the latency figures are an average latency per hit, taking into account every time an instruction executes across all analyzed wavefronts. In addition to the latency figures, there's also a bar representing the latency. The length of this bar is relative to the latency of all other instructions, so a longer bar represents an instruction with a higher average latency. The bars are color-coded to let you know if any of the reported latency was hidden by work performed on other wave slots while the subsequent instruction was waiting to be issued on the current wave slot. Portions of the bar that are green indicate that VALU work was being performed on other wave slots. Yellow portions indicate that SALU work was being performed. Portions that are red indicate that no other work was being performed and there was likely a stall. The Details panel provides additional information about the selected event, including providing a visual wavefront timeline for the event, instruction hit counts, and hardware utilization bar graphs. For indirect ray tracing events, there is an extra UI control at the top that lets you view instruction timing data for any shader function in the ray tracing pipeline. The shader functions are sorted by the overall instruction cost percentage. When you select an export name from this combo box, the ISA view will quickly scroll to show timing data for that shader function. While the instruction timing view shows you data collected from all analyzed wavefronts, it also provides a way to filter the view to show only a subset of wavefronts. To do this, you can use the wavefront latencies histogram. This histogram shows you the number of wavefronts analyzed and plots all wavefronts according to the total duration of each wavefront. Here we can see that for this ray tracing event, 988 wavefronts were analyzed. They ranged in duration from 1,805 clocks up to 276,934 clocks. Looking at the histogram itself, we can see that most of the wavefronts were at the lower end of this distribution, meaning they were relatively fast. However, there are some wavefronts that took quite a bit more clock cycles to execute. Using the slider control below the histogram, we can filter the wavefronts. Here we have set the filter to only include the 20 slowest wavefronts. When we do this, all the data shown now represents just these 20 wavefronts. The wavefront timeline in the Details panel has also been updated to show where in the lifetime of the event these 20 wavefronts were executed. By filtering wavefronts, we can analyze the performance characteristics of our slow wavefronts and compare them to the fast wavefronts to see if we can understand why some are slower than others. We can even take this a step further and use the wavefront latencies combo box to filter the view down to the slowest or fastest wavefront in the current selection. When we do this, the view is updated to show data for a single wavefront. One final thing I want to show in the instruction timing pane is a feature that is specific to ray tracing pipelines. This is the call targets table. For ray tracing pipelines using the indirect compilation mode, the compiler generates function call and function return instructions, allowing control to flow from one function to the next. These instructions are indicated by a special glyph in the ISA view. When you select one of these instructions, a call targets table is populated in the Details panel. This table shows a list of targets for the selected instruction. Each entry contains the name of the target, the number of times the target was called by the current instruction, and the type of the shader. You can click on any entry in the table to quickly navigate to that target in the ISA pane. This allows you to follow the control flow through your ray tracing pipeline. That wraps up the RGP portion of this talk. While RGP can answer many questions about the performance of ray tracing events within a frame, it cannot answer performance-related questions about the acceleration structures used in the dispatch rays events. To help answer these questions, I'm happy to hand off to John, who will now preview the Radeon Ray Tracing Analyzer.
Thank you, Chris. Hi, I'm John Alper, and first, let me say how proud I am to be able to show a preview of the Radeon Ray Tracing Analyzer. Unlike all of the previous Radeon Developer Tool Suite applications, I will be using its acronym RRA going forward. RRA allows you to get a deeper insight into your ray tracing game. This presentation assumes that you are familiar with the basic concepts used in real-time ray tracing. In particular, we will be talking about acceleration structures. So if you're unfamiliar with this concept, there's a good article on Khronos' website. With RRA, you can load acceleration structures, or bounding volumes, that you can acquire from Radeon Developer Panel. Once you load these structures, you can leverage the specialized views to pull apart your scenes and understand the performance costs. You can move through your scenes with RRA and get a real-time visualization of the same traversal used in your game. Once you load your trace in RRA, you will land on the TILAS viewer. This view displays the TLAS information associated with the trace you've captured. Let's go through the contents of the TLAS viewer. On the left, we have the tree view. This component lists out the nodes in the acceleration structure and allows you to interact with them directly. To change the TLAS, you can use the drop-down on the top left. Just under the tree view, you can get information about the selected node, such as the extent of the volume and surface area heuristics, as well as node-specific information, like the instance transform. On the center top, we have the coloring modes. These coloring modes visualize various information about the scene using the 3D viewer. Just under the coloring modes, we have the 3D viewer itself. Below, we have the depth slider. This slider allows you to specify a depth range to visualize bounding volumes. We have the rendering controls to the right side, and just under that we have the camera controls. So that is the layout of the TLAS viewer. We also have a BLAS viewer that shares the same layout with minor differences. Before we dive deeper into the viewer, let's talk about statistical navigation. You can click on the BLAS list tab on the top left to bring up the list of all the BLASs in your currently selected TLAS. In some cases, you may need to navigate your scene by using numbers. Specific BLASs may have attributes that may allow you to distinguish them easier from the rest of the scene. The BLAS lists allow you to sort BLASs by those attributes. For example, you can sort by the maximum surface area heuristics to iron out triangles that may cause performance issues. You can also sort BLASs by their depth to get a faster look into the most complex elements in your scene. Let's go into one of these BLASs by double-clicking. As I mentioned, the BLAS viewer is very similar to the TLAS viewer. Let's talk about the camera and navigation. Games are unique in their map design, and this uniqueness means that the way you move around your scene needs to be diverse and adaptive. To aid your navigation around the scene, we have two camera modes. The default camera control style is CAD. Using this mode, you can rotate around a focal point. The movement in this camera mode will move the focal point around the scene. We also have an FPS camera. The FPS camera style allows you to fly around your scene from the first-person perspective. You can use the drop-down under the camera style to pick a style that matches your needs. Scroll down on the right panel to get more information about the selected camera inputs. Depending on your game's layout, your scenes may be oriented with a different up axis or inverted in vertical or horizontal axes. To align the camera to your scene, you can use the toggles we have just under the control style. You may also use the U key when the up of your camera is oriented towards your game's up axis to adjust the orientation settings automatically. In some cases, you may be interested in specific coordinates within your game. You can enter the camera position directly under the camera orientation settings. Let's move on to the bounding volumes. Exploring the bounding volumes may reveal information about your scenes that may help you optimize for a better ray tracing performance. The bounding volumes are hierarchical, and this hierarchy means that bounding volumes may contain smaller volumes. These smaller volumes will be at a deeper level of the acceleration structure. You can click and drag across a range in the depth slider to display the bounding volumes at those depths. For the TLAS viewer, the volumes go all the way down to instance level, and for BLAS viewer, the volumes will go as deep as the deepest triangle node. One problem here is that the geometry in your scene can occlude bounding volumes as you explore. Simply disable the render geometry and wireframe overlay toggles in the rendering controls panel to get a better look. Usually, it is more intuitive to interact with the nodes through the 3D viewer. You can click through the viewer to select instances in TLAS viewer and triangles in BLAS viewer. Doing so will highlight the node you selected in the viewer and on the tree view to the left. If you'd like to navigate to your selection quickly, you can use the F key. Pressing it will focus the camera on your selection. Given the complexity of modern games, you may need to declutter your scenes to focus on specific parts. In our array, the simplest way of decluttering is to toggle individual nodes through the tree view on the left. When you click off the checkbox next to a node, it will disappear from the scene. Please note that the hierarchical structures underneath a given node will also become invisible. You can also select volumes that are not instances or triangles in the tree view. One convenient way of selecting parent or child nodes of the currently selected node is to use the arrow keys when the viewer is not highlighted with the blue border, and the selected node has a blue background in the tree view. We also have some other convenience features in our right-click context menu. For example, you can filter the scene to only display your selection. We've opened this BLAS through the BLAS list panel. We have a very similar workflow here for quick navigation back to the TLAS viewer. On the top left, you can open the Instances tab to view all of the instances of this BLAS in the currently selected TLAS. You can double-click on an instance to jump and view it in the TLAS viewer. Now that we are familiar with the viewer, let's go over the coloring mode utilities in our array. Coloring modes are visual indicators that can answer various questions about the scene. You can select the coloring modes through the drop-down bars just above the viewer. For example, as you're exploring your scenes, you may be interested in distinguishing between various node types. For this, we can color the BVH by volume type, which is the default BVH coloring in our array. This mode will assign specific colors to each node depending on their types. Using the Settings panel, you can assign a color of your choice to each node type. You can access these settings by opening the Settings panel at the top right corner and selecting Themes and Colors. You may also change other settings here, such as wireframe and background colors. If you're interested in the depth of the nodes, however, we have the tree depth coloring. When you're in this mode, the colors of the bonding volumes will be arranged between blue and red depending on their depth. If you have a single level selected, volume colors will reflect the absolute depth in the hierarchy. If you have a range of levels selected, you'll be presented with the root of the range as blue and leaves as red. In the TLAS viewer, we have a total of 14 geometry coloring modes. Each coloring mode will provide a unique insight into your scene. We have a subset of these modes available in the BLAS viewer. If you'd like to get more information about a coloring mode, you can hover over it in the drop-down menu. You can also check out our documentation by clicking on Help on the menu bar. Here's a quick demonstration of the geometry coloring modes. Given the nature of complexity in the acceleration structures and the specifics of the traversal algorithm that traverses these structures, it is often difficult, if not impossible, to imagine the final performance costs of a given scene and its setting. To aid you in understanding the performance costs in a more intuitive way, we have the traversal counters. Before we get deeper into the traversal counters, let's note that these values are emulated on the fly and are not the same as those you can view through RGP. RRA terminates the counters on the closest hit. Your game, however, may launch subsequent rays after the initial closest hit. RRA also counts the custom intersection volumes as a single unit. With that said, you may still greatly benefit from reducing the traversal count signatures through editing BLASs and strategic instance positioning in the TLAS, since the subsequent rays will also go through these same acceleration structures. It's also worth pointing out that the traversal counters in RRA do not require actual ray tracing hardware. To enable the traversal counter visualization, check the render traversal counters under the rendering controls. Doing so will disable the render geometry, since these views are incompatible. The traversal counter visualization depends on the range provided by the user. Also, the range of each counter may vary with the layout of the scene and the observer's perspective. As you change the counters while moving throughout your scene, you will need to adjust or reset the slider located under the render traversal counters toggle. Like the rest of RRA, blue means a lower count, and red means a higher count. Let's start with the loop count. The loop count is the number of iterations the ray performs on the acceleration structure. It allows you to identify parts of your acceleration structure that are the most taxing for your rays. These iterations may include traversing deeper into the structure or eliminating volumes. Across all the counters, the loop count will have the highest number range. On the other hand, the instance hit counter is bound to have a smaller number. Instance hit counter is essential in terms of understanding how the instance positioning affects the traversal time. As the ray traverses into the scene, it is optimized to discard bounding volumes as needed. The ray can discard a volume if a suitable triangle candidate has been encountered and the volume is behind this candidate. This process dramatically speeds up the ray traversal since the ray does not need to traverse into unnecessary volumes. However, when the ray hits an instance node, the context switches into the BLAS. This means that the ray has to trace the entire BLAS to answer the closest hit to compare against a different node on the TLAS. If instances overlap, the ray must wait until each instance is properly checked. That is why the ability to view instance hits may help arrange instances throughout your scene to reduce context switches of the rays. Another way to understand the traversal specifics on a given acceleration structure are the box hit and box test counters. Some parts of the acceleration structure may be denser depending on the perspective. These denser parts may overlap such that the ray will not be able to discard volumes to optimize traversal duration. The box hits and box tests provide a way to view this optimization gradient. And finally, we have the triangle hits and triangle tests. As the ray traverses, it may encounter triangles in an unspecified order. If the ray hits the triangle, it will compare it against the best candidate triangle, aka closest hit. If there are no candidates, this triangle will be assumed as the best candidate. The triangle hit in this context is the number of triangles that we've used as the best candidate triangle. In contrast, the triangle test is the triangles we've tested for a hit throughout the entire traverse. The traversal counters, especially loop counter and the instance hit counter, are very powerful tools, since they can visualize your scene's unintuitive and hidden performance costs. To wrap up, we have a suggested workflow for you to get started. Once you open your trace, get comfortable by setting up your camera. To get a faster turnaround, we suggest that you fly around your scene using the loop count traversal counter. Using the counter range slider, you can visually identify the objects that stick out. When encountering an object that causes high loop count, switch between various other coloring modes to get more information. In this example, we can visually confirm that the instance overlap are not the main reason for the high loop count. We can switch to geometry rendering and pull apart the scene using the tree view to investigate further. Max 3 depth and triangle count geometry coloring modes suggest that this BLAS is not an outlier in terms of complexity. Once we confirm that this is an anomaly, we can further isolate in the BLAS viewer. You can double-click in the viewer or click on the BLAS address to switch to BLAS viewer. Viewing this object in the BLAS viewer through loop counters reveals that the volumes that enclose these long triangles in the structure occupy a significant amount of screen space. Since similar triangles are stacked next to each other, the volumes cause a high increase in the loop count. You may have noticed that the center part of the structure does not suffer from the same issues. This is because the triangles in that part of the geometry are closely aligned with the XYZ axes. This alignment means that the bonding volumes are occupying significantly less space. The immediate strategy you can use to lower the loop count footprint of this BLAS is to split it up into instances. Using your preferred modeling tool, you can split the triangles into groups and rotate the non-axis aligned triangles in a separate mesh. Once these triangles are separated, you can import them back into your game with corrective transformations. Separating the BLAS this way will introduce a small instance overlap, though in this case, this small sacrifice will save the rest of the rays that pass near the overlapping volumes from overspending traversal time. Here, we have duplicated the same issue on the previous BLAS and provided the equivalent suggested solution. These geometries consist of very thin triangles stacked in the Y dimension. On the left, we have a single BLAS that has the non-axis aligned triangles alongside axis aligned triangles. On the right, we have two BLASes. These BLASes have been instance transformed to match the single BLAS on the left. However, all the triangles in these BLASes are axis aligned. When we switch on the traversal counters, it becomes clear that the single BLAS on the left has an exponentially larger loop count over the BLAS on the right, even though they're visually identical. If we adjust the slider on the BLASes to the right, we can observe the instance boundary that the transformed BLAS occupies once it has been transformed in the TLAS. We can also observe the instance overlap by using the instance hit counter. Unfortunately, this is only one of the many cases that you may encounter as you explore your scenes. But by using the combination of features in our array and with the new ray tracing features in RGP, you can identify then resolve your bottlenecks and improve ray tracing performance. That wraps it up for this quick preview of the Radeon Ray Tracing Analyzer. For more information and updates on our tools, follow us on GPU Open. And thank you for watching.